fraud. So I will start by talking in general about robotics. So it's a famous quote that says that in 50s, it was predicted that in 5 years, robot would be everywhere. In 60s, it was predicted that in 10 years, robot would be everywhere. And in 70s, it was predicted that in 20 years, robot will be everywhere. And in the 80s, it was predicted that in 40 years, robot will be everywhere. So this shows the shift in the expectation of the advancement of robotic. It's a cool quote. But I want to argue today that actually we are at the verge of the golden age of robotic, and soon robots would be a common sight in our daily life. For instance, if we look at the recent advances, either in US or China or Europe, they are all like remarkable. And I predict that a Sputnik moment for robotic plus AI is on the way. So we have quite a bit of advantage in the recent years on large data set, RL, large language model, and other generative AI algorithm. But the application of AI mainly remains to, the application of AI to robotics remains limited. In fact, there is a famous quote that says that I want AI to do my laundry and dishes so that I can do my art and writing. So this basically needs AI plus robotic. But when you look at the AI community in general, the focus there is on the average accuracy. And this is not compatible with the most basic 3 rules of robotics that was written in novels by Isaac Asimov, that a robot should not harm human, a robot should obey the order unless it conflicts with the first one, and also protect itself unless it's conflicted with the first two. And as you can see, the current state of the AI is not compatible with robotic because it's mainly focused on the average accuracy and it has a black box nature. So as Farad mentioned, I'm establishing currently a laboratory. It's called CAS Lab. And our goal is to fuse ML control and sensing into intelligent system to achieve the result that each field cannot achieve independently. So there are both encouraging and discouraging examples. These are two good examples that I always mention. One is that the Google data center cooling, where DeepMind was able to reduce the billing of the cooling center by 40%. When they use AI correctly in a physical system. And there's also a discouraging example, like Boeing 737 MAX 8 crashes in 2018 and 19, which caused life loss and billions of dollars loss in terms of money. So to ensure the safe operation of autonomous robot system, the research strategy of our lab is grounded in the deep analysis of the problem, the nature of available data, a specific constraint for each application, and uncertainty quantification. So in our lab, we design algorithms that are mathematically rigorous, physically intuitive, and practically implementable. And we test this algorithm on research platform to evaluate their performance and also explore new design. At the moment, we are in the process of ordering these two platforms. One is that going to be soon here. It's called Blue ROV from Blue Robotic, and we are planning to do experiment at RIT Tape Reserve. And the other one is Unitary go to W for traversability and multi-agent interaction research. So if I want to review what I tell you is basically that our focus is on building the brain of the ball. And we basically work at the intersection of electrical engineering, computer science, and mechanical engineering. And we basically work on closing the feedback loop from sensing to signal processing to machine learning, uncertainty quantification, decision-making, control, and actuation. So from methodology standpoint, we design novel machine learning algorithm, data-driven optimization and control algorithm, and a statistical signal processing algorithms. And in terms of application, we have 3 areas. We focused first and foremost on autonomous robot system, where artificial intelligence and robotics come together. And the aim is to increase safety, security, and efficiency of this system. We also work on autonomous underwater vehicle and applied ocean science. The main aim there is to have autonomous data collection at sea. And I also work on quantum engineering. Our goal there is to improve the performance of the quantum devices. So if I have time, I will show you some of the results that we have done in each of these areas today. So we'll start by safe learning in robotic. So these are the 2 critical considerations for taking a robot to real world. One is that we want to learn online, relying on the stream of the data. And the other one is that we want to ensure the control objective despite the uncertainty in the learning algorithm. So I have been in ships and doing experiment in San Diego in Pacific Ocean, and this is from personal experience. When you work with surface vehicle, you have GPS and you have wireless communication. If you go work with the shallow water device, you have acoustic communication or ACOM, which is going to be with band limited, it's going to be with delay, with packet drops. But when you go to deep ocean, or even you can think about exploratory mission in other oceans of the other planets, it's going to be basically no communication or with so much delay and such a limited bandwidth. So as you go down this road, we have more uncertainty and less structure, and we have more lack of infrastructure and service. And in such cases, autonomous robot systems are of great interest. So let me start with just telling you about the general area of how we can apply AI in decision making for robots, and then I will delve into specific examples. So we developed safe learning enabled planning and control algorithm for autonomous robot system, and we want to achieve we want to avoid forbidden areas, meaning that the robot wants to achieve individual safety, and also we want to avoid collusion with the other robot, meaning that the robot wants to achieve joint safety. So let's just start with an example. We have a robot here that is in the safe state shown in white, and it want to reach its goal position shown with the star. While it's doing, you want to avoid the unsafe region that is shown in red, and the robot doesn't know some of its parameter or frictions or parameters from environment. As an example, you can think about like an autonomous car that it goes from one surface to another surface, or you can think about an robotic in Amazon warehouse when the amount of load on the robot changes. We also, by studying this problem, answering the fundamental issue with reinforcement learning, that they do not provide any formal guarantee of safety. And if you do the training directly on the hardware, it could bring hardware damage to the hardware, it could bring harm to the human operator. So this is something that I learned when I was working with engineers at JPL, that whenever you want to design such an autonomous system, it's a good practice to think about an autonomy stack. So you have high-level planner, mid-level trajectory planner, and low-level controller from low frequency to high frequency. So high-level planner is going to run in low frequency. It could be like reinforcement learning, and the output is going to be the waypoint usually. And then in the mid-level planner, once we have the waypoint, we want to make trajectories for the robot to go from waypoint A to waypoint B. And usually model predictive control is used. And also we have low-level controller that actually interact with the physical world. And that needs to be run in high frequency. At all these three layers, we have sensing, control, decision-making, and safety need to be ensured that all these three layers. So I'm going to briefly discuss some of this today, and this is the whole, we study all of them in our lab, but I just want to focus today on the low frequency controller for this part of the presentation. So we assume that the baseline control policy is provided, and we want to focus on the low-level controller. So the philosophy that we follow is of George Box, that all models are wrong, but some are useful. So we design safe learning enabled model-based control algorithm, and we do uncertainty quantification via Bayesian learning. So in short, I'm going to show you how we can do these two things, that we want to develop efficient Bayesian learning algorithm to obtain the distribution over system dynamic, and how we can use the learning distribution to optimize the system behavior. So let's just start with an example. It's an Ackermann-derived vehicle model. It's a string in this geometrical model that represents a string in the car. And let's assume that the Ackermann car vehicle trajectory is shown with the dashed blue, and the two obstacles are shown in red. And we are going to consider two cases. One is that we do no learning, meaning that we're only going to rely on the prior knowledge. The other one is that we are going to update the system dynamic estimate using the data collected so far when we do online learning. So I'm just going to show you some numerical example, and then we are going to delve deeper on the concept and some mathematical idea behind it. So with the no learning, we have the prior knowledge on system dynamic, and we have large variance, and the car could not move between the two obstacles. But once you do the learning, you gather the data online, you could reduce the variance and allow the car to pass between the two obstacles. So let's look at the mathematical formulation. So if you want to work with some model, that unknown model, we can assume that the robot has following some dynamic, right? That x dot is equal to fx plus gxu. X is the state. It could be position, velocity, acceleration, other states. And u is the control input that we are providing to the robot. And this is called nonlinear affine control system because f and g are nonlinear maps, but u is the effect of u and the whole dynamic is affine. It just get multiplied to g and it will be added to the whole dynamic. In fact, here f is called the drift term and g is called the input game. And you can write this dynamics, which is a good model for bipedal car, for car-like robots, as matrix capital F, which is made of fx and gx times 1 and u, or we call it underline u. We want to study the problem of enforcing probabilistic safety. I will take in a moment what I mean by probabilistic safety. Then both f and g are unknown. Again, think about the warehouse example, or think about the multi-tenant reversibility. And in this part of the talk, assume that the obstacles are known, but results have been extended on top of this work. And basically, if you don't know the unsafe set, you could use a LiDAR to detect the obstacle and find the smallest convex set that is going to contain the obstacle. And the reason that we want to find the smallest convex set is that we want to solve this in online, so we want to be efficient. So what we are going to do is that we assume that we have a Gaussian process trial belief on the dynamic. We assume that the vectorized version of f of x, which is going to be obtained by stacking the columns of f and g on top of each other, is distributed according to vectorized of m0x, the mean of the Gaussian process, and k0x and x prime. So k here is the kernel, and it shows that how x, a point in the state, is related or correlated to another point on the state, x prime. And it's problem dependent, but it's basically modeled the correlation. And if you have worked with time series, you are like familiar with Gaussian process, but this is a little bit more complicated than a regular time series because f, the dynamic, is a function of x, and x is a function of time. And assume that you have a nominal control policy pi of xk provided to us. As I mentioned to you by now, is that our aim is to modify this online policy, which might be provided to us by reinforcement learning algorithm in a minimum invasive manner to ensure safety with probability pk. And pk is a user-specified risk tolerance. So basically, we have this following chance constraint formulation at time tk. We want to project this policy that is given by us by variable planner to UK, while we ensure that safety happens with probability bigger than PK. And this PK is the user-specified risk tolerance. If it's for autonomous driving, it should be of order of 10 to the power of -8 to beat human driver. So it's pretty tough problem. But if it's for underwater autonomy, if it's for autonomous farming, or off-road driving, there is going to be more forgiveness, and this probability could be lower because there is more room for error. But at the same time, also there is less infrastructure, and there are more challenging and exciting problems for learning there. So I'm going to discuss the probabilistic safety constraint for robots. So recall that the dynamic was x dot equal to fx times underline u, and we assume that we have a Gaussian process belief on the state. So I'm using Gaussian process here because Gaussian processes are a universal function approximator, and not only they are going to provide an estimate of the mean, but also provide the estimate of the variance. So we have the following training data on the position, on the control input, and on the derivative. This data might be noisy or not. So usually how you gather this from a robot is either using an INS, inertial navigation system, internal navigation system that you work using IMU, or you have an anchor in the environment and you send a signal using a LiDAR, and using a range-based measurement, you find what is your position, what is your velocity, and the control input is known because we apply it to the robot. So this is a tough learning problem because we want to learn two functions, f and g, from a single set of data. And in general, there might be correlation between the different components. But when we study this problem, we notice that most of the literature assume decoupled Gaussian process per system dimension. So what we have done here is that we developed an efficient learning algorithm using matrix variate Gaussian process, and we put in a specific factorization, a computationally efficient factorization for this kernel matrix to be B0 canonical product A. And that using this factorization, we were able to model the correlation among the different components of the system, and it has the similar computational complexity, but it provides greater inference flexibility. So I don't want to go to the details of this algorithm for now because I want to talk about other things, but if you are interested to know more about it, let us talk offline. So one of the most popular method currently for ensuring safety, either in control, advanced nonlinear control theory or robotic, is something called control barrier function. So usually it's used in the literature with known dynamics, and it's using this function h that is positive in the safe set shown in white, and it's negative on the unsafe set shown in red. And this control barrier function usually works with criterion that is defined as follows, which is basically the lead derivative of h with respect to the dynamic plus alpha times h. So alpha here is a positive constant, and lead derivative of the h with respect to dynamic is just the gradient of h times the dynamic. Here we want to ensure safety by letting CBC is bigger than or equal to 0, so it provides a lower bound on the derivative of h. So it's basically telling your robot that when you are moving to your goal position, take actions to ensure that your h stays positive. So it's basically dynamically enforce the safety constraint. But usually in the literature it's with known dynamic, but here we are going to use it with a random dynamic. So we are taking derivative with respect to a random field, which could be a more challenging problem. So if you do that Gaussian process regression that I mentioned to you, so you started with the prior, you gather the data, now you have a belief or posterior over the data that could be calculated. And then we can, using the updated knowledge of our dynamic, we can think about how we want to solve this chance constraint formulation. We wanted to project this policy to the closest safe action UK while ensuring safety with the probability bigger than or equal to PK. So we are basically going to replace that with this control barrier criteria. So this is where the canonical structure of control theory meets with machine learning. And we have been made sure that when you have this Gaussian assumption of the dynamic, the CBC is going to be a Gaussian random variable with a mean that is linear in U and quadratic, and a variance that is quadratic in U, which is quite important. Because you can use this property and write this probabilistic chance constraint as a deterministic constraint in terms of the means and variance of this criteria, control barrier criteria. So when you do that, you actually get a optimization control based controller, which is the QCQP, quadratically constrained quadratic program. But when we wanted to solve this, we noticed that in many cases, the problem is not efficient and could not be solved online. Because if you look at it, it's not going to be always a convex criteria. But there is a paper by Stephen Boyd that shows that any QCQP could be written as an SOCP, and SOCP could be solved quite efficiently. So I'm going to move to the next part soon, and I just wanted to mention that I simplified the presentation here a lot for this talk. First of all, I want to talk about first order system. In general, like robotic system have many or related higher relativity. And if you are interested, you can read about the case of bipedal or car-like robot in our paper. And also, I didn't talk about the liveness property. So in general, you don't only have safety, you have another criteria for liveness or to ensuring that the robot is moving toward the point that you want. And when you have more constraints, solving the problem is more challenging because it becomes easier, because it might be easier for it to become infeasible. So there are like discussions in the paper, and I'm happy to talk with you offline about this. So let's just wrap up this part with doing another numerical example. So we are going to compare the enforcement of CBF in two cases, in mean CBF and base CBF. In the mean CBF, we are not going to account for the variance on the system dynamic. In the base CBF, we are going to gather data, update the variance, update the uncertainty about the system dynamic. So as you can see in the left, when you work with mean CBF, the car is going to have a crash with the upscale because it just works with the average knowledge, what usually people do in machine learning. But when you have the base CBF, the car is going to be a slowdown on the right, gather data, and it could go between the two obstacles safely. Another work that I have done when I was at Caltech with my colleagues there is that we extended this result to navigation in unstructured environment. So here, assume that you have a robot shown in blue, wants to navigate from a start position and just achieve a random core position shown in yellow star, and it wants to avoid the collision with the other agents shown in red. We assume here that approximately half of the other agents are belonging throttle toward the random chosen goal, and the half of the other agents showing some degree of collision avoidance behavior. And in such a case, uncertainty in the prediction of other agent trajectories is inevitable. And so such an algorithm is actually quite useful here. So you can see here the sample pass of what was known, the state of the art, and you could see the sample pass with the learning. So the robot learns to avoid the obstacle and safely achieve its goal. So it's an navigation in a structured environment. Yeah, all of this is happening online. We gather the data online, we update the model, we do the optimization online, and so it's quite promising. But I just also want to talk about a result which is quite recent. This is a recent paper that we published since I joined RIT with my colleagues at University of Maine. So I wanted to briefly also discuss this because it's related to this topic. So one of the issues with Gaussian process is that they are not actually quite scalable. So that's one of the main bottlenecks of uncertainty quantification. Several approximations exist. We actually use the approximation in our previous work, but they provide kind of a trade-off. And this is actually a famous meme in X, the previous Twitter, that says that this is how the world would look like if Gaussian process was scalable. And we were like having thinking about this for a long time, that is it possible to have a learning algorithm that is efficient, but could do uncertainty quantification or distance awareness error similar to Gaussian process. So the reason that Gaussian process is so popular for safety critical system is that it provides something that we call distance aware uncertainty bound based on the distance from the observed data. And what happened typically is that your uncertainty is going to increase when you go to the regions that is far from training data to reflect the reduced confidence in the predictions. So to talk about that is it possible to make a distance-aware neural network? Let's review a theorem. There is this famous theorem by Kolmogorov and Arnold. It's called Kolmogorov-Arnold theorem, or CAT, that says that if you have any multivariate function, f of x1 to xn, you can really write this as a superposition of continuous single-valued function or univariate function, or you can think about them as activation function in neural network with addition. So there has been quite a bit of debate that is this theorem is going to be useful for machine learning or not. In fact, there is a paper in 1989 that is entitled says that Kolmogorov theorem is relevant. And there is a paper in 1991 that is entitled says that Kolmogorov theorem is relevant. So the main reason that there was this debate is that when you look at this activation function or univariate function, and you want to build the network on top of that, the functions are not nice, and in fact, they are erratics. But this is the recent paper that came at 2024 from MIT that keeps this Kolmogorov-Arnold theorem structure, but with more layers. Instead of just having 2 layers, it's going to have more and more layers, and use splines as activation function. So I don't know this author actually, but the paper came where I was still at MIT, and unfortunately, sometimes it's got a bad rap because it doesn't very, it kind of lacks the true literature review, and it doesn't connect well to some of the known literature. But I personally think it's very nice case study. And because of this paper, I think Spline have a comeback, and let me show you why. So if you look at the name Spline, it's originated from flexible wooden strip used by shipbuilder. So the spline have these knots or contour points that need to be fixed, and a curve is going to interpolate between the knots. And what we have seen here is that we could model the spline neural network as a semi-parametric model. So we don't work, we basically modified the paper CAN, the model that was given to us by CAN, by assuming that this knots or contour point is a subset of training data. In this way, we can combine the accuracy and computational efficiency of parametric models such as neural network and analyzability of non-parametric models such as GP. So we have used this property to develop a distance-aware uncertainty estimator for CAN. So our paper is published in ICAST. This is an ongoing work. But basically what we have done is that you replace the CAN, the spline neural network, with this new design that either simultaneously or offline, when you train the neural network, you can also calculate the error on the confidence of the neural network. Basically, we replace the blocks of neural network with these new blocks that has the prediction error, has the prediction. Also, it provides a way to calculate the error at knobs and also the interpolation error. Two of the main challenges that we have in this result is that finding the Lipschitz constant of the network is challenging. And the other one is that propagating the error between the layers is challenging. As I said, this is an ongoing work, but we have an early publication and it is quite nice. And here is a comparison with Monte Carlo and Gaussian process. We have started with the worst case for now. So it's worst case analysis. So it's more interpretable than traditional neural network, and it provides the distance-aware uncertainty bond, similar to Gaussian process, and it's much more efficient than Gaussian process and Monte Carlo ensembles. And I think it's going to be an amazing tool for robotic, but we will see how it goes. We're very at the earliest steps. So I also want to talk about cyber-physical system security. So this is another area of interest for us. So we have this emerging field in robotics called cloud robotics and autonomous system, where the cloud is going to enable the robot to use shared resources such as big data and machine learning to improve their performances. But when you study such a problem, you notice that the distributed nature of the system is the Achilles heel. It's a source of vulnerability to cyber attack, and most of these systems are actually relatively easy for sophisticated hacker to get into. And to ensure the safe operation of system, we need to address the physical security in addition to cyber security. So one of the famous kind of these attacks is man-in-the-middle attack, when the attacker sits between the plan and controller and act as a fictitious plan for the controller to show that everything is normal, and at the same time it acts as a malicious controller for the plan to destroy the plan. So it's like Ocean 11 movies that they wanted to rob a bank. They pre-record the normal operation of the bank and they replay it when they were basically robbing the bank. And so I usually focus on the positive side of what machine learning and control and sensing and integration of this field could bring us for us. But here I also think about from an adversarial point of view. So here we basically develop a new kind of attacks on cyber physical system and a defense way for them. So instead of just recording everything and replay it for the authenticator or controller, in this case, the attacker tried to eavesdrop the system initially, learn system dynamic, and then go to the hijacking phase. And we have shown that this is code actually beat the replay attack, which is the system theoretic model of the Stuxnet malware. So what we have done is that we studied this kind of attack on the system, and we analyzed the attacker's deception probability for any control policy when the attacker used arbitrary learning algorithm to hide itself. And we provide, we prove that the controller can prevent such security breaches by superimposing a privacy enhancing signal on top of the nominal control policy. So we want to ensure that the physical layer is safe, even if the cyber layer is broken. So I also want to talk very briefly about what we do in quantum, only in 3 slides. And then I just want to talk about the underwater work that I have done at Scripps, and I'm continuing here at IT. So you could also ask that what are the implications of learning, control, sensing, integration of these fields in quantum domain. And if you study a quantum system, you will notice that there are 3 major market opportunities. One is advanced computing, the other one is ultra-precise sensing, and the last one is secure communication. And the main goal in this community is that we want to achieve quantum advantage, meaning that we want to have this system that work in tandem with classical system, but they should outperform eventually a classical system. So when you also study this problem, you will notice that you are still looking at the cyber-physical system, which I call quantum cyber-physical system, because the physical system here is very different. It's basically a quantum dynamic, such as a superconducting qubit. So here is the research diagram of how quantum technology works from Australian Army Research Center. So we have the qubit, we have the system, we have a measurement system, and we have a classical computer that is run to control the system for us, and it takes us from any initial condition to any final condition. When you study quantum system, you will notice that the successful application of many of the quantum devices actually also depend on the control of their dynamic. And there are certain properties for these dynamics that we need to account for. There are both opportunity, and at the same time, there are challenges. It's called superposition, no cloning theorem, entanglement, and quantum measurement. So while I studied this problem for a year and a half, what I was thinking mainly was that how the techniques that we have recently developed in data-driven optimization, control, and ML could be applied to these systems. So the main challenge to me in this problem is the quantum measurement. It's an interaction with the real world, and it could alter the state of the quantum device. And also the result of the measurement is not determined. So there are two ways to go with this. Either you go with open loop scenario, basically you calculate everything offline and then apply it to the system. This is the main way used in industry currently. Or you do with closed loop scenario that you would have some sort of measurement that is called non-demolition type of measurement. And actually, this is a quite interesting problem. And in 2012, the physicists and engineers who were able to measure and control a single quantum system win the Nobel Prize that year. So it's a quite challenging problem, but it has so many applications. You could use it for countering the error in quantum computing. You can realize quantum gates again in quantum computing, and you can also enhance quantum sensing performance. And but when you study this problem, you will notice that the dynamics of the system are also not known in reality. And when they interact with larger system, the knowledge become more and more less. And but the control is quite more challenging. So one example that I usually give is that you could think about a robot, but the robot goes to a tunnel, and at the end, basically during the time that the robot is in the tunnel, you don't know about the state at all. And at the end, also you are not able to measure the state. You are only able to measure the probability value. And it's much more involved. So you need to do, one of the ways to do this is to do two processes called quantum state tomography and quantum process tomography. So basically you run the experiment many times and you observe all these probabilities. And you do a quantum state tomography, which is called tomography because it's similar to tomography in medical science. So you try to gather and understand what was the state before it collapsed, before the measurement. And then also you do quantum process tomography to understand what was the path that the state has been taken to go from the initial condition to the final condition. And after that, you can get to model and you can do the learning and other things. So also I want to finish by talking about some of the things that I've done for underwater at Scripps and what I'm doing currently at RIT as a follow-up work on those. So now I want to discuss with sensing and how integration of sensing, machine learning, control could bring for us and robotics. So when we study ocean science in underwater acoustics, there are two important problems. One is forward problem. When you want to understand sound propagation in the sea, when you have parameters, and from parameters, you want to go to the acoustic data, why? And also you have the inverse problem, where our goal is to inform geometric, oceanographic, or geoacoustic information from acoustic signals. So you have a data, which is the acoustic field that you receive, and you have a parameter X that you want to estimate. One of the toughest problem here is called geoacoustic inversion. The aim here is to characterize the undersea environment, such as the number of seabeds or sound speed from these acoustic signals. And it's quite helpful because it enables the prediction of sound propagation in underwater environment, and it has many applications. For instance, Navy is quite interested in this problem because it helps the sonar performance forecasting. And also it's important for understanding the noise pollution at sea. because humans are making an increasing level of noise and have an adverse effect on the animals and ecosystem of the ocean. So let me discuss about this problem in more detail and how I'm going to relate it to what I usually do in robotic AI. So let's discuss this problem in more detail. So we have the source here that could be told from a ship, and it transmits a signal of frequencies between 50 to 400 hertz. So these frequencies have been specifically chosen to ensure that the sound is going to penetrate to the surface and to the different sediment and mud stone layers. And why here is the received signal? It's the received pressure of the field on the hydrophone. So it's basically hydrophone or water version of the microphone. And we have a VLA here, which is a vertical linear array of these receivers. And we assume that we have a model why the observed pressure is just Fm plus epsilon. Epsilon is the observation noise, and Fm is the undersea acoustic model, which could be evaluated with various different numerical ways that is out there. We use the problem called Kraken for this problem. And our aim is to characterize the parameter n, which could be like water depth and sound speed from the received signal on the hydrophone. So the inversion problem are usually imposed because usually the number of parameters is larger than the number of observed signals. And also the forward map is a complicated nonlinear mapping. And one of the ways to go about this is doing Bayesian inversion. That you have a distribution called posterior distribution that enables uncertainty quantification and help us to analyze the diversity of potential inverse solution. But it's hard to sample posterior distribution. The state of the art that it's used is usually Monte Carlo Markov chain, MCMC, which is a powerful technique for estimating the posterior distribution. But if you have worked with MCMC, you will notice as you increase the number of parameters, as you increase the dimension, they soon become inefficient. For instance, for this example, sometimes people use pretty powerful computers, but they run it for 2 weeks, 3 weeks to be able to find good posterior over the parameters. So let's see how this is related to underwater robotic. So if you look at the data collection at sea, usually what happens is that previously it was using surface or undersea manned vessel, and it was quite costly and work intensive. So the ultimate goal that we have here is that we want to do this sort of inversion on an autonomous platform, and we want to do active planning for marine robotics. Basically, we want to design information seeking autonomous data collection at sea algorithms, and that help us to maximize information gain for tasks such as geoacoustic inversion. So there are two things that need to be done. One is that this platform, either either the one on the top or Albert 3 or the one that we are working at RTB, they don't have the computation tools there. So first of all, usually you need to integrate the processor there. And the other issue is that the processor that you will add is going to have computational limitations. So there is not much room there. And also battery power and other issues. So for this case, for this reason, estimation method with attractive computation cost is quite important for this system. And it's essential for deployment of autonomous platform. And as I mentioned to you, MCNC is the current state of the art, but it's quite computationally expensive. So what we have done here is that we propose to use invertible neural network that I will discuss with you in a moment. And we are working on increasing the efficiency of INN at the time and autonomous platform. Also, we develop an algorithm called invertible symbolic regression that is more concerned with safety. And this is one of the first work here is called invertible symbolic regression. It's a 2024 paper. So this neural network is called invertible neural network. I don't know if you are familiar with it or not, but it's quite interesting subject. It's a particular class of learning algorithm. It was developed around 2016 to 17, and they are a bijective map between input and output. So once you learn the forward model, the backward model also will be trained at the same time. So you can solve the inverse problem much easier. But when you solve the forward problem, usually you lose some of the information. So if I take a photo with a camera from this room, while this room is in a 3D world, I'm going to have only a 2D amount of information. I'm going to lose some of the information. So to counteract the loss of information during the forward process, we also incorporate a latent variable z to the neural network. So x is the parameter, is the unknown, y is the observation, and z is the latent variable. So we have the forward modeling from x to y and z, and we have inverse prediction from y and z to x. So the invertibility of this INN came from the structure. So they are built using, usually using this affine couple layer. So they are made from a sequence of reversible blocks. So if you look here, we have the data input U. You can divide it to two parts, U1 and U2, and let U2 to go through some functions, S1, T1, that could be arbitrary complicated function like neural network. U1 doesn't change at the first phase, just get multiplied to output of S1, and it get added to output of T1. And then you reach to V1 and V2. And at the same time, again, you let V2 go through some functions, some neural networks, and you then again multiply to V2 and add it to V2 again. So if you want to write this in forms of equation, these are the equation that you will get. But it's really amazing that these blocks could be easily reversed. So if you look at the left, we have the forward process. If you look at the right, we have the inverse process. And for doing that, it's just enough to reverse the direction of the horizontal array and also replace plus with minus and multiplication with division. So this is also the equations for the inverse direction. But notice that when you are inverting the coupling, you are not inverting the subnetworks Si or Ti, S1, T1, S2, T2. They are always run in the forward direction. So what we are currently doing is that we are training this neural network for this ocean data, and we are using the ocean model that we have. And then you can sample Z, the latent variable, to be a Gaussian random variable. And once you train the network, it could help you to efficiently sample the posterior distribution over X. And we are currently working on this to improve the performance of INN to be as good as MCMC. We have some promising results that I should be able to show you soon. But in terms of computation, it offers great computational efficiency. Because if you have sufficient training that could be happen offline, you could do real-time sampling very fast because you don't need to do any training either. You just need to run the network in the backward direction. But one thing that we should point out that the distance or the area that you are working with, the characteristic should be similar to the area or data that you feed the network with and do the training before. So it shouldn't be so much discrepancy between the two. And we're also developing an algorithm called invertible symbolic regression, where the aim is to have some sort of equation model instead of black box machine learning when you want to use it for safety critical applications such as robotics. So instead of basically having black box model, we also try to have a white box model. It's in my usual interest to like design learning algorithms that you can also quantify the uncertainty or do a sensitivity analysis with, so you are sure when you want to apply it to the real world. So what we do here is that we want to achieve interpretability with via symbolic distillation. So having a set of equation could be quite useful. It could give us insight beyond the output of the neural network. But usually when you want to solve this problem, it's quite challenging, the symbolic regression, because the function space could grow exponentially with the dimension. So what we have done to have a set of equation for the application that we have is that we use a computationally efficient method. There is again another work called equation learner network that was developed in 2016. It's a fully connected neural network, but instead of using traditional activation function, EQL adopt elementary function that could be learned from the physics of the problem, like sine, exponential. And also when you do the training, you try to enforce the sparsity. And it could be a parameterized neural network that if you choose the activation function right for your problem, it could be learned quite efficiently, and it could be quite useful. So what we have done is that we also take this to the inverse problem, and we have been able to design invertible architecture can replace both forward and backward model. So for the forward model, we estimate the forward process with an analytical surrogate model that is actually diffeomorphism. Diffeomorphism is a mapping that not only is differentiably continuous, its inverse is also differentiably continuous. And we demonstrate and be able to demonstrate the role of different components, either from measurement quantity y or the latent variable z to constructing the posteriors over x. Just want to finish by saying that if you are excited about robotic, try to take my class in the fall. It's E585 or 685. And this is one of the projects that one of my students has done in the class. As you can see, he is like quite successful to do the mapping and the robot could navigate safely. And if you want even one more challenge, also take the course that follows that is taken by Fraud. It's called Advanced Robotics. So we have quite exciting opportunities and tools and people for robotics in RIT. So I hope your time you could use some of that. Yeah. Thank you.